In most cases, when we are only dealing with theory, sometimes what we are actually doing is hard to understand. That is why most of the time we end up having to make sure that at least we get some examples or some questions that are relating in what we are doing. So here I have a sample of questions. There are two questions, and question one is based on the first derivative test, and question two is based on the second derivative test. So the first question in here, let me try and zoom it in and see what we're actually going to get. Let me place it 125. Okay, 150. Okay, if you look here, the first question is saying, in each of the following functions, find the interval or intervals, if there are many, where the function is increasing and where it is decreasing. So I'm going to take this function and answer this question, and then the second question in each of these functions is saying, use the first derivative test to classify the critical points. So the first thing that you can see here, I want you to understand that the first question and the second question, both of them are actually talking about the derivative. So we have to take the first derivative in both these particular questions. So I want you to copy these questions, and then after copying these questions down, and then after you have done that, try and solve them using the theory that we actually were actually explaining in the previous lessons. And then after you have done all of that, then you can continue to see if your answers are actually matching with the answers that I am getting in this here. So just copy this, and then after that we will try and solve, because I might not get time to keep going back and forth to check what the question was saying. I will just try and continue to solve. So we have question number one here. So our question number one, we have A, and A is saying that we are having our f of x, and f of x is equal to x cubed, and then we have minus 6x squared, and then we have plus 9x, and then from there we have a nice plus 1 there. Now the first question, which is Roman figure number one, is saying, in each of the following functions, finds the interval where the function is increasing and where it is decreasing. So the first step that I want you to do is to find the first derivative of this function here, and then once you are done with this particular function here, you will actually end up saying that, okay, sure, let's take this derivative. So we are going to have the first derivative of this is going to be 3x. We bring this 3 down, subtract a 1, 3x squared, minus 2 times 6 is going to be a 12x, and then we subtract a 1, so we'll end up with a 1, and then we have a plus 9. So that's what is actually happening. That is the first derivative. The second step here, I want to set this derivative equal to a 0, so we'll end up having 3x squared minus 12x, and then plus a 9, and then I want it to be equal to a 0. And then once we are done with that, remember this is not a manual, I'm just telling you the steps. First you find the first derivative. The second step is to set the first derivative equal to a 0. And then once you are done with that, you try and actually solve for x here and see what you are actually getting. Of course, I have a 3 here. 3, 12, and 9, we have a common factor of 3, so I can factor it out. And then after factoring it out, I will be left here with x squared. And then here I'll be left with minus a 4x. And then I have a plus here. And then I will have a plus 3, all equal to a 0. And then, of course, 3 times 4 is a 12, and then 3 times 3 is a 9, and then we have this 3, so this is fine. And then after that, I'm going to divide by 3 throughout, and then I will end up having x squared minus 4x plus a 3 is equal to 0. And of course, you can factorize this nice thing here. The first way is to find the factors of 3. You know that a plus or minus 1 is always going to be part of whatever this factor is. And then secondly, we also know that this factor here plus or minus 3 are also factors of this 3 here. So we wanted to find the factors of this that are actually making it equal to a 0. So if I'm plugging in here, let's say I am plugging in a 1 here. So I'm plugging in a 1, I will end up having 1. I will end up having 1 squared is equal to 1, minus 4 times 1 is 4, and then plus a 3. What am I actually going to gain here is the fact that if I have this is going to be 1 plus 3 is going to be 4, 4 minus 4 is going to be a 0, which means that x is equal to a 1 is one of the solutions of this. In other words, x minus 1 is one of the factors of this. So I will have x minus 1, and then this side, I don't know what you are actually going to get, but the nice thing about this whole thing is that you will actually end up having x squared divided by x is going to be x, and then 3, positive 3 divided by minus 3 is going to be a minus 3. So that's how you factorize this. And the nice thing about this to be 0 is either x minus 1 is equal to 0 or x minus a 3 is equal to 0, which means that x is equal to 1 or x is equal to a positive 3. So these are what I call the critical points for this particular function here. So once you are actually having these critical points here, remember that we set the derivative equal to 0. And now, what are the values of x that are going to make this undefined? I mean, this first derivative undefined, because this is a polynomial, is defined everywhere. So these are the only critical points. The next thing that you actually do, you want to actually draw what I call the number line. So this number line of ours is going to be a nice number line. Of course, I will try and make sure that it is nice. So we have this because we are having two critical points there. Once we have this, the smallest number is going to be 1. The largest number is going to be a 3 here. So the next thing that we wanted to find out here is this nice thing here, because this function here is actually defined everywhere. So this number line of ours, because we want to find when is it bigger than 0 and when it is actually less than 0. So we are not, we don't really care much when the function is actually going to be equal to 0, because we already know that it's going to be here. So we don't care much, so we put our open our holes there. The next thing that we wanted to find out here is this. If you don't place those holes, you're not going to be penalized here, because the most important thing here, we just want to find out where is it positive, where is it negative. So the next thing that we'll do, we'll pick a number somewhere in this region. The number that is less than 1, I'm going to pick a 0. So 0 is one of the numbers. And then I pick the number here that is between 1 and 3. I'm going to pick a 2, of course, because this is a number between 1 and 2. And then I pick a number that is bigger than a 3. I'm going to pick a 4, of course. And then after I've done that, I take this number 0 and then I plug it in the second derivative. So if I am plugging this number here, bear in mind that this is just the same as 3 times x minus 1. This is x minus 1. And then here I'm going to have x minus a 3. So this and that is the same thing, because that's how we ended up factorizing it to be like. So if I take a 0 and I plug it here, I will get a negative 1. So I'll end up getting a 3 times a negative 1, and then here I will get a minus a 3. So I will get 3, which is positive, times a negative, I'll get a negative number, times a negative, I will get a positive. So plugging in a 0 here is just telling us that we will get a positive. And then the next thing, let me write this here. So we have 3 times x minus 1, and then we have x minus a 3. So if I take 2 and I plug it here, 2 is actually going to be bigger than 1, so I will end up having 2 minus 1 is going to be 1. So I will end up having 3 times 1 times, and then if I plug in a 2 here, I will get a negative. So I will get a negative 1. So I have a positive times a negative. I will end up getting a negative. So in this interval, whatever I'm going to get is a negative. And then I plug in a 4 here. If you look into this here, if I plug in a 4, 4 minus 1 is going to be a 3. So I'll get a 3 times a 1. So this is positive, and this is positive. Positive times positive is actually going to be a positive. What does this thing actually mean? This thing is actually telling us something like this. So if you look in this interval here, this interval starting here, because we're going all the way to negative infinity, and this side we're going all the way to positive infinity. So if you look from negative infinity up until you arrive at 1, you are actually realizing that this function here, the positive, means that the first derivative is positive. In other words, the function is increasing. So in this interval, f is increasing. Positive means the function is increasing. And then if you look carefully into this, when you look at 1 and then go all the way up until you arrive at 3, you are actually having f is decreasing because the first derivative is negative. So negative means the slope is going down, so it is the function is decreasing. And then if you look at from 3 up to positive infinity, you can actually see that f is increasing function. So f is increasing in this interval and that interval. Bear in mind that I'm not using square brackets here, because at this point we know that the first derivative is actually 0, and also that means actually the function is changing from increase. Here it's changing from increase to decrease, and then here from decrease to increase. So there is nothing happening here. The function is not increasing, and also it is not decreasing. So we cannot include this point and we cannot include that point. Hence, we are using open brackets. That's how we actually solve this particular function. Now, this particular question, the second question was nicely saying that you, in each of the four, find the intervals where the function is increasing and where it is decreasing. And then the second one is saying use the first derivative test to classify the critical points. So what is actually needed here is this. We do have a critical point. So this point here is a critical number. So this is a critical number, and this one also, it is a critical number, because the critical number is where the first derivative is equal to 0 or it is undefined. So we have this critical number here and that critical number there. So the first thing that I want us to find here, if you look into this, if x is equal to 1, which is one of the critical numbers, then f of 1 is going to be equal to, so you go to the original function now. So the original function was saying we are having x cubed minus 6 x squared plus 9x plus a 1. So we're actually having a nice thing here, which is 1, and then we place a cube there, and then here we're actually separating. We have a 6, and then we have a 1, and then we square it, and then we go and say plus 9, and then times 1, and then after that you add a 1 there. Of course, you're going to get a 5 here. So we are actually having here f of f of 1 is equal to a 5. So once you are having this here, the question is this value here a local maximum or a local minimum or neither? So that is actually what is important here. So using this information that is in this table here, the function is increasing, and then nothing happens here, and then start decreasing. What is actually happening in this particular function? So the function is increasing. When a function is increasing, it's going up, and then after that we arrive at some point here where x is equal to 1, and then nothing is happening there, and then the function starts decreasing. Now the question is this point a max or is it a mean? So you can see that this point is actually bigger than any other point that is close to it. So we are actually having here a local maximum, a local maximum. That's what we wanted you to actually find here. And then the second one is saying if we are actually having x is equal to 3, because that was also another critical point here. So when you are having that, what will be our f of 3 then? So we'll have f of 3. What is f of 3? So if we're plugging in here, we're just gonna change that and plug in a 3, and then we go all the way here, change that and plug in a 3, and go all the way there, and then you change that and then you plug in a 3, and then that is going to be a 1. Now the next question is saying is this the local mean or is it a local maximum? So the next thing that you actually need to go to, you need to go to this number line here, which means that when you are at 3, x is equal to 3. So we have x is equal to 3 at some point somewhere there. Before that, the function was actually decreasing, so it was decreasing, and then when it arrives at that particular point, because we have a negative, so negative, it means the function is decreasing, so it decreases and decreases and decreases, and then when it arrives there, it starts increasing, it starts going up. The question is this a mean or is it a max? So if you look at this point, around the points that are close to it, it is the lowest point. So this one here is actually a local minimum. So that is what we expected from you. You don't compare this one and that one, because this one is so far compared to this. We just wanted to find this. Is it a local mean? Is it a local max? The same thing for this particular point. So that is what you actually say. You just say at x is equal to 1, we are actually having a local maximum, and at x is equal to x3, we're actually having a local minimum. So that is what was expected in this particular question. And then now we go to B, and of course our B was very nice. It was saying that we are having this nice function here, 1 over 3x cubed minus 2x plus a 5. So here we are actually having our f of x, and our f of x is 1 over 3x cubed, and then after that we have minus 2x, and then we have a plus 5. Of course, the first step, because we first wanted to find out where the function is increasing and where it is actually decreasing. So when you look into this function here, you will find out that you need to first find the first derivative, which is when you're multiplying this by 1 over 3 times 3 is going to be just a 1, so we are going to have x raised to 2 minus a 2, because that is the first derivative of this, and this one, the first derivative, is equal to a 0. And then the next thing that you need to do, you need to set the first derivative equal to a 0 and then solve for x. And if you look carefully into this here, you will find out that we are actually having a nice thing here, which is you can either take x squared and say it is equal to 2, and then after that you take the square root on both sides, and then of course this one here you will get a plus or minus x is equal to a square root of 2, and then after that your x is equal to plus or minus a square root of 2. So if you look into this part here, you have two critical points. One is minus square root of 2, and the other is actually the square root of 2. And if you look into this one is defined everywhere, so we don't have any value of x whereby this function is undefined. The next thing that you do, you draw a number line with these critical values that you are actually having here. How many of them? We have 2. One is square root minus square root of 2, and then the second one just the square root of 2. Of course, at these points, the first derivative is equal to 0, and which means that the function is doing nothing, it's not increasing or decreasing, so we don't include those 2 points. And then the next thing that you need to do now, you pick a point that is less than the square root of 2. What is the square root of 2? Just wondering, what will be the square root of 2? Where is the square root now? The square root is here. So we have a 2. This is actually minus 1 comma something. So to be safe, just pick a value that is so far from this. I'm just gonna pick here minus 5 and then plug it in the first derivative, and then the value between this one and that one, I know this is positive, this is negative, which means 0 must be between the two values, and a value that is bigger than this, I'm just gonna pick a 5 to be safe and then plug it. Where are we actually plugging these values? We are plugging them in the first derivative. So our first derivative was this, so I'm going to write it here. So we're actually having f prime of x is equal to x squared minus a 2. And then of course, if I take a 5 and plug it there, I have a nice thing here. I have a minus 5 and then I square it up, and then after that I want to subtract a 2. What am I getting? I get a positive number. That's what is important. I don't really care about the value. I just want to know, is it positive or negative? So we have a positive, and then when I'm plugging in a positive 5, what am I getting? It's still positive. So if I'm plugging a positive 5, I'm still having a positive there. And when I'm plugging in a 0, what am I actually getting? I am getting a negative, or a negative 2. So now I have this nice thing here, which is actually saying to us something like this. Is saying that this is the next step to find where the function is increasing. So if you look here, because we have a negative infinity this side and a positive infinity this side. So if I'm moving from negative infinity, I'm moving from negative infinity up until negative square root of 2. Of course, I'm not going to include this point because at that point the function is doing nothing. And then when you look at negative infinity, we cannot touch it. That is why we're not including it. We are having a positive here, which means the function f is increasing in that interval. The function is increasing. And then if you look at the second interval here from negative square root 2 up to the positive square root 2, we have a negative. In other words, the first derivative is negative there, which means our function f is decreasing. That is what you need to know. And then from there, you can also see that in the last interval there, that is from square root 2 up to positive infinity, the function f, the first derivative is positive. In other words, function f is increasing. That is what is important here, because you want to find those intervals where the function is increasing or decreasing. Now, the second question, which is Roman figure number 2, Ewart was asking us this nice question here, which says, use the first derivative test to classify the critical points. So what is actually happening at this value and at that value? Of course, what you need to realize here is this nice thing, that if, let's say, you have x and x is equal to minus square root of 2, then our f of negative square root 2 is equal to this. So you go to the function. The original function was this, so we had 1 divided by 3, and then of course you have this minus square root 2, and then this whole thing here, you wanted to give it a cube, so we're going to give it a cube, and then after that we say minus 2 times x, which is square root of 2, and we wanted to have a negative there. And then after that you can close, and then you say you're gonna add this 5 here, so we have a plus 5 there. So the answer we're actually getting here is this thing here. So the answer we're getting here is actually 15 plus 4 root 2 all over a3. So that is the answer that we're getting. And then if, let's say, x is equal to positive square root 2, our f of square root 2 is equal to. So here I'm just going to remove the negative there, and then I go all the way here, and then I remove this one. I'm going to get a 15, and then I have a minus 4 root 2 all over 3. But the question here is saying classify. So when they are saying classify, they are saying use is this a local maximum or a local mean? That is what is important here. So if you look into this value here, you will find out that the function is changing from increase to decrease. So it's going up and then it start coming down. So at this point here, because a function is goes at x is equal to square root minus square root 2, the function is going up and then down. So this point is bigger than all of them. So here we are actually having a local maximum. So this one here, this point here, we are actually having a local maximum here. So most people usually want you to say at. This is how they usually prefer. I don't want to end up losing marks unnecessarily. You will say that at square root 2, and then they take this thing here and they say 15 plus 4 root 2 all over 3. We have a local maximum. So that's what they want you to do. But if you say this f of x is equal to this, I also believe that it is correct. But other people prefer you to just show that this is actually the point you are talking about. They want it in a coordinate system. The same thing. What am I doing now? The same thing here. They want you to say at square root 2, and then you write this number here, minus 4 root 2 all over 3. We have a of course, let's go to square root 2. So if you go this here, the function is decreasing, we have a minus, so it's going down and then start coming up. So it's something like this. When the function is decreasing, it's going down like this, and then it arrives at 2 and then start increasing. So what is happening at that particular point? Because this point is the lowest, which means it is the minimum. We have a local minimum. So we have a local minimum at that particular point. Let's go to C. C was saying we're actually having f of x, and f of x is equal to x to the power 4 minus 4x cubed. The first step is this one. Wanted to find the interval of increase and the interval of decrease. So want to find the first derivative. The first derivative is going to be 4x to the power 3. Bring this down, subtract a 1, minus this multiplied by that is a 12, and then we have x, subtract a 1, so we have a 2. Of course, we can see that we have a 4, and then we have a 4, so I can take out a 4, and we have x squared. I can take out an x squared because it's common here and there. Once I take x squared, there I will be left with x, and then this 4 is gone, and then 2 x's are gone. I'm left with 1. 12 divided by 4, we know that is a 3, and then this one here is already taken out. So that is what is important here, because you're multiplying this, it's going to get a 12, and then this x squared is going to go there, and you're getting that. And then the next thing that you want to do now is to set the first derivative equal to a 0. So want to set this equal to 0 so that you can get critical points. So once it's actually happening, once you're actually having that, you can see that for this to be equal to 0, either 4x squared is equal to 0 or x minus 3 is equal to a 0. And if you look into this particular part of this solution, we're actually seeing that x squared dividing by 4 on both sides will get x squared is equal to 0 divided by 4 is just a 0. Also that if I take square root on both sides, I will just get x is equal to a 0, whether I like it or not. And then this side, I will get x is equal to a 3 when I'm taking it to the other side. So once you are actually having these two, which means now you have the critical points. Once you have critical points, you can draw your nice number line, and then you mark your critical points. How many of them? We have 2. So the first one is 0, the other one is a 3. Of course, we don't include these points because at those points the function is actually the first derivative is actually equal to a 0. And then we know that this one goes all the way up until it arrives at negative infinity. This one goes all the way until it arrives at positive infinity. And then if you look into this part here, then we pick a value. So the first thing that we need to pick a value that is less than 0. So negative 1 is one value. And then the value between 0 and 3, we know that's supposed to be a 1 or a 2. And then a value between 3 and infinite, we can pick a 4. I mean, the next value. So once we do that, we just take this number and then we plug it here. So if we take this number, we plug it there, what are we going to get? We are going to get 4, and then what is that number there? It's going to be, I have a -1, and then I want it squared, and then inside I'm gonna place it as it is, and then I'm subtracting a 3, and then I want an answer. The answer is saying we're getting a negative here, so we get a negative number. And then after that, I'm going to plug in a 1. I'm going to plug in a 1, which means remove the negative there. I remove a negative there. So we get negative again. So we are having a negative here. So just to confirm what is actually happening here, we are having a negative because this one here is always going to be positive. It's only this part that is deciding. So all these values that I'm picking are actually below these 2 points. Then the next thing that we actually end up getting here is just we pick this 4 and then we plug it there. So when we're plugging in a 4 and then we go all the way here, we get a 4 also there. You can see that we're getting a positive, right? So what is actually important in this particular function is this nice thing here, that if you look into this these two this we have this, we have that, and then we are actually having this over here. So basically this function is saying some of these things here, that if you are moving from negative infinity up to 0, the function f is, because we have a negative, is decreasing. And if you look from here, which is 0, you're moving from 0 and you're going to 3, you can also see that the function f is still decreasing. So we have a function that is still decreasing, and then you go for this one here, this interval here, and you can actually see that from 3, positive 3 up to positive infinity, the function f is actually increasing because we're having a positive first derivative, so it is increasing. I want to explain something here because someone might be tempted to say that let me make it red, from negative infinity up to 3, because they want to say that this function is decreasing from negative infinity up until you arrive here. What about that point? Because there is something that is happening at that point. The function is not increasing and it is also not decreasing. So this one is not 100% correct unless you say that unless you say that this function is decreasing from negative infinity up until you arrive to 0, and also from 0 up until you arrive at 3, because now using this union you say that 0 is not included. So this one will be correct, but this one is actually not correct. So this one is correct, but this one is not correct. So that is why I am writing it like this. And also, now if you look into this here, you can actually see that we are at we're still at number 3. Okay, we're at Roman figure number 2 now. So if you look at Roman figure number 2, it is saying that classify use the first derivative test to classify the critical points. How do we classify these critical points? Another thing that I want you to actually realize here is that there is actually something that is actually happening that is actually confusing us from here, because is this a critical point or is it not a critical point? Because we want to use the first derivative test, because the first derivative is saying if you are moving from increase to decrease, that's a max. If we are moving from negative to positive, if the first derivative is moving from negative to positive, that's actually a mean, and also from positive to negative is actually a max. So what should we actually do? For instance, here if you look at this particular point, you will notice that the function is decreasing, and then it seems to want to change from decrease, and then if you look there, it still continue with the decrease. So you might find out that the function was decreasing something like that, like a cubic for instance. So in most cases, if let's say I were to draw a cubic and it goes like that, at that point it was trying to change, but it never really did change. So we cannot actually say at this point there is a change from decrease, because it's still increasing and then continue to increase. But in this particular case we have a decrease, so it's going down, and then maybe it was starting to change and then still went down, so it was trying to change. So at this point here, you can actually see that there is actually no local mean or max, so we cannot have a conclusion here. So what we can actually say here, if x is equal to we have 0, we have f of 0, which is just excuse me. So we're actually having, where is this? We plug in the original function. So if I'm plugging in a 0 here and I'm plugging in a 0 here, we're actually having a 0. In this particular case, all you need to say is that no local mean, minimum, and no local what am I writing here? No local maximum. Because at this point here, the function was not changing from decrease to increase or from increase to decrease, is from negative to negative. So whatever was happening here is just telling us that the function wanted to have a change, but actually the decrease was so strong that it never gave it a chance. That is why we're still having no local mean and also no local max at this point. So if you want to write it in a very professional way, you can say that at 0 point, when x is equal to 0, y is equal to 0, no local minimum or maximum. So there is nothing of this. And then we look for the second one here. So if we're saying we have x and our x is equal to in this particular case here, we have x is equal to e3. So we're actually having a 3 here. What is our f of 3? Of course, our f of 3 is going to be 4. No, it's not a 4. It's going to be actually 3 raised to 4, and then we actually subtract a 4, and then we multiply this by a 3, and then of course we raise it to a 3, and then we have a minus 27. So if you look into this one here, we're actually having a minus 27, right? So we can say that at when x is equal to 3 and y is equal to minus 27, we go back to the number line and see we are changing from decrease to increase. So the function was actually going down, decreasing, and then started to increase in whatever way. So this point is the smallest. So we have a local minimum. So minimum means the lowest. So we're having a local minimum at x is equal to 3. Decrease to increase. That is what is important. So we were at number C. Let's go to number D. What was number D saying? Let me check here. Number D was saying we are actually having f of x is equal to e to the power minus x squared. So here we are at D here. So we are having at D, we have our f of x, and our f of x is equal to e raised to minus x squared. So what is the first step for this? Because we want to find out where is this function increasing and where it is actually increasing. So the first step that we actually have here in Roman figure number 1, we actually want to say that, can we first find the first derivative of this function here? The first thing that I want you to realize here is this. It's easy to take the first derivative of this whole thing. So if you actually want to know, of course, if you wanted to still you want to find out more about how to find the derivative, of course there are some lessons on that. For now, I'm just gonna give you just a shortcut here and deal with this whole thing. You must be fit at this stage to take out the derivatives. So I have e raised to the power something. So if this function was e to the power x, the derivative of this function was going to be e to the power x. But in this case here, we don't have x, so we are actually going to have this minus x squared in the place of x. So e is just gonna take this whole thing as it is, and then after that we multiply by the derivative of that thing that is sitting in the value of x, which is minus x squared. So this whole thing is going to say that we have e raised to minus x squared, and then what is the derivative of that is actually going to be minus 2x. So this whole thing is actually telling us that we are actually having a minus 2x times e raised to minus x squared. So that is our first derivative of this particular function. Now the second thing that we wanted to find out here, when is this function going to be equal to 0? So you set minus 2x times e raised to minus x squared, and then you want it to be equal to a 0. So that is actually this is actually the first step that you wanted to actually look at. So the next thing that I want you to realize here is this nice thing here. When is this thing going to be equal to a 0? I want us to deal with this thing piece by piece. So we have a multiplication here, so we have some nice brackets here. So whatever this x is, it will give us a real number here. So the question is this: is it possible to have a constant here which is positive, and then you raise it to some number there? I'm gonna call it, let's say that number is equal to u. So if you are having this nice thing here, is it possible for an exponential function to be negative? That is the first thing that I want us to look at here. So if you look into this thing here, whenever you have a number e and you have a number e here, no, not this one, alpha. So if you have a number e here and then you raise it to a negative number, whether it's a 10 or it's a 5 or whatever are you going to get? You can see that you will get a positive number. Whether you can raise that number and place a 50 there, this number is always going to be positive. Even if you say it's minus 500 and something, the number you're going to get is, of course, it will never be 0 because it's just that this function is decreasing and decreasing, and this thing is actually just rounding this thing off because I cannot deal with it. That is what is actually happening here. So we're having this number is always going to be positive. Let me explain here what is happening. If let's say this here was positive, this function was going to look something like this. So it was going to grow and grow like that. But now when you are having a negative there, the negative is actually telling you that this negative that is actually there is actually telling you that because this one is always going to be positive, so you are getting a negative number, which means as we're going this way, we're supposed to be decreasing. So let me just put this one is e to the power x, and then I want to talk about e to the power minus x here. So if we were having this nice thing here, we're actually going to see that, okay, as this function is actually going this side, it's going to go down all the way because as this x is increasing, this is actually getting smaller. So we're going to end up getting something of this kind. So this one is e raised to minus an x. So whether this exponent is negative or is it positive, this function is always going to be above the x-axis. These are the x-axis, these are the y-axis. So whether I'm pulling in here and I'm adding an x squared here, this function here is always going to be above the x-axis. So what is actually happening with this function is that e raised to x squared is always going to be bigger than 0. It will never be equal to 0 for this particular case here, because this one here, if we talk about this is always going to be a positive number. X squared is always going to be positive. Even if we are picking a negative numbers, this is always going to be positive. And if let's say now I am actually adding that negative, it means that the exponent is always going to be a negative number. So as we're going all the way up, this is actually decreasing, and also this one, as we are getting to more negative numbers, going to be decreasing, which means the increase is around this 0 here. But what is important is this: whatever that value is, this will never actually get to 0. So this part is always going to be bigger than a 0. So basically, when is this function actually going to be equal to 0 is actually when the other part is equal to 0, because e to the power s can never be e raised to power something is not going to be equal to 0. That's not really possible. So that's something that I want us to actually realize, that in this particular case we're actually going to end up having minus 2x equal to 0, because this cannot be equal to 0. And then if you look into this part, we'll end up dividing on both sides. So we have minus 2x is equal to 0. Then we divide by minus 2x, minus 2, and then divide by minus 2 this side. And of course, we actually end up having x is equal to a 0. So this is the only critical point we are actually having here. So we have x is equal to 0 here as the critical point. So we have a 0 here. Of course, 0 cannot be included because the first derivative is equal to a 0 there. So the function is not doing anything. And then this side we have a positive infinity. So if I am plugging in a value here which is negative, right? So I'm going to pick a value here less than 0, let's say minus 1, and then a value bigger than 0 will end up picking a 1. And then if I take this value and I'm plugging it here in this first derivative. So if I am plugging it here, I will get, if I take this, I will get minus 2 times minus 1, which is going to be a positive 2. Whatever I'm gonna do here, if I'm plugging it here, I will still get a positive thing. it's not gonna be negative at all, because it's e raised to something. Even if it was 5 raised to something, this is an exponential function that is always above the x axis. And then for this part here, this is this is actually the identifier if we are getting a negative or positive. So if I'm plugging in a negative, negative times a negative is going to be positive, so this part is actually going to be positive. And when I'm actually taking this value here, 1, and I'm plugging it here, I will get a negative times a positive. I will actually end up getting a negative. So which means that this function here, we can actually see that from negative infinity up until 0, we can see that f is increasing. So we have increasing function. And then from 0 up to positive infinity or just infinity, we can say that f is decreasing because we have a negative there. F is decreasing. Now, from there, we go to actually a Roman figure number 2, which say classify this. You can see that the function was moving from increasing to decreasing, which means that we can say that at x is equal to 0, so we're having x is equal to 0 here. So at this point here, we are looking for f of 0. So if we can go to our original function, which is e raised to that, we'll end up having remember that our original function was it was f of x, it was equal to e raised to minus x squared. So if I'm plugging in here a 0, I will end up getting e raised to minus 0 squared, which is the same as e raised to just a 0. So a raised to 0 is just a 1, so we're actually having a 1 here. We can say that at this f, or we have or because this one has a local. Let's look into this. The function was increasing, positive, increasing, and then it came down, decrease. So we have a local maximum. So that is what is important here. What is also important here when you are describing the critical point, this point here, you get it by taking this and plugging it in the original function. But when you are testing for the number line, this point that you get here, you plug it in the first derivative, and this point you plug it in the first derivative. It's only at this stage whereby you're plugging in the original function. Make sure that you actually understand that very well. Let's talk about the last question in number 1, which is e, and then we're actually having our f of x is equal to the natural log of x squared, and have a minus 1 there. So what is important here, want to answer the first question, which says that when is this function increasing and when this function is actually decreasing. So if you look into this function here, the first thing that you actually need to realize here, you want to find its first derivative. What is f prime of x? So how do you take the first derivative of this function? We know that if, let's say, our f of x was equal to ln of x, the first derivative of this function was going to be 1 over x. So that was going to be the derivative of this particular function. But now we are not having, so if we're having this derivative was just gonna be 1 over x, but instead of x we are having x squared minus a 1. So because that what is inside here is not x, we want to multiply by the derivative of what is inside, which is x squared minus a 1. And then once you do that, of course, you can see that we are actually having 1 over x squared minus 1 times, what is the derivative of that? Is going to be just 2x, and the derivative of that is going to be a 0. And this nice thing here is going to be a 2x, and then divide by x squared minus a 1. And then from there, you can see that you are actually having f prime of x is equal to that. That is the first derivative that we are actually having. So what is actually the next step for this? The next step is saying that we want to find where f prime of x is equal to a 0. So we are having 2x divided by x squared minus a 1 must be equal to 0. And of course, if you look into this, once the denominator is equal to 0, this whole thing is going to be undefined. It's not going to be equal to a 0. So the only time this whole thing is going to be equal to 0 is when 2x is equal to 0, or when the numerator is actually equal to a 0. So what you actually need to realize after getting this whole thing here is that this nice part here is telling us that for this thing to be equal to 0, I need to divide this side by 2, divide that side by 2, and then this one and that one will cancel out, and we'll have x is equal to 0 over 2 is just going to be a 0. So that is one critical number that we are actually having. The next step that we need to find here, what are the values of x that will make the first derivative undefined? So we want to find out when is this whole thing gonna be undefined. It's going to be undefined when the derivative is actually equal, I mean the denominator is equal to a 0. So we are going to end up having x squared minus 1 is equal to a 0. This one here, this one was saying we wanted this to be equal to 0. Now we wanted this or that to be undefined. In other words, we want the denominator to be actually a 0. So once we are having that, you can actually see that when we're factorizing this, we will end up having x minus a 1, and also we'll have x plus a 1. We want this equal to a 0. The next thing that you want to do, when is this whole thing is actually going to be 0, is when this equal to 0 or that equal to 0 or both equal to 0, which means that when x minus 1 is equal to 0 or x plus 1 equal to 0, in other words, when x is equal to 1 or when x is equal to a minus 1. So we are having also these two critical values. So what is actually important now that you are actually having these two critical numbers? So then the critical numbers we are having here is a combination of these two and also the ones that we have above. Of course, this number line is moving from negative infinity to positive infinity. The first critical number here is minus 1, and the other one here is here we have a 1, and then the one that we got by making the numerator equal to 0 was just nicely sitting here. It was a 0. Let's take a note here that our f prime of x is equal to 2x divided by x squared minus 1, and then the original function, which is f of x, it was equal to the ln function of x squared minus a 1. Now let's talk about this and see what we're actually getting. So if I pick a value less than minus 1, it's going to be a minus 2. Of course, a value between minus 1 and it's going to be a 0.5 or 1 over 2, negative 1 over 2, and then here we'll have 0.5 or 1 over 2, and then a value above 1 is going to be a 2. Now if I take this, remember when we're testing this first derivative test, we use the first derivative, not the original function. So if I take a value here, which is minus 2, and I plug it here, I will get a 2 times minus 2. I'll get a negative in the numerator. In the denominator, I'll get 2 squared is 4. 4 minus 1 is 3. So I'll get a positive number. Negative divided by positive is going to be a nice negative here. And then again, this one is negative, so in the numerator I get a negative. Here we are getting a number which is 2, which is bigger than a 1. So 2 squared is 4. 4 minus 1 is actually going to be a 3. So of course 3 is positive, so we have positive and a negative. So when you're dividing these or multiplying them, you get the negative. Now let's look at a minus 0.5. If I take a 0.5 here, which is negative. This in the numerator is going to be negative. Of course, we're going to have a negative here. When I'm plugging 0,5 here, 0,5 is the same. We have 0,5 is 1 over 2. When I am squaring this, I will get 1 squared divided by 2 squared, which is the same as 1 over a 4. 1 over 4 is a quarter. Quarter minus a whole thing, or a 0,25 minus 1 is going to be a negative thing. So we have a negative here. Negative divided by negative, we will get a positive here. So we have a positive. Now, if I take this one here and I plug it in the numerator, it is positive. So we'll get a positive in the numerator. If I'm taking this 0,5 and I'm plugging it here and I subtract a 1, I will actually end up getting I have 0,5. 1 over 2. 1 over 2 is going to be a quarter, and then a quarter is less than a 1, right? So we'll get a negative. So positive divided by negative, you can actually see that in matter of fact here, you will end up having a negative here. And then let us actually plug, let us plug now a 2 here. Here we'll get a positive, and here we'll get a positive. So here we're actually getting a nice positive. That is what is important here. Have a positive. We have this one is going to be 2. 2 squared is 4. 4 minus 1 is 3. So we'll also end up having a positive. Positive over positive is that. So looking into this sketch here, you can see that the function from negative infinity up until you arrive at minus 1, we are actually having goes all the way, we're actually having a decreasing. Because it's negative, we have a decreasing function, right? And then if you look at a value that is actually between this function, I mean between 0,1 and a 0. I want to talk about this whole thing here. And then if you look at value between 0 and a 1 there, I want us to talk about this at a later stage, but I want us to talk from 1 up to positive infinity. So we are actually having here the last one, we are moving from positive 1 up to positive infinity. You can see actually that this one is saying that f is decreasing. That's what I wanted to say. And then here we're having f, because it's positive, f is increasing. So the first derivative is positive, so the function is increasing. So according to this here, if you move from negative 1 up to 0, the function is saying the function is increasing. So f is increasing. I don't want to write this with a red. I want to write it with a green. So f is increasing. And if you look into this function here, here we are having a 0, and then here we are having a 1, and then you can see that you are having f, because this one is saying negative, which means the function is decreasing. So we are having f is decreasing. Now the question is, why am I actually taking time to actually look into this? The first derivative is saying this thing. If this function here is actually defined, then in that interval it is actually increasing. If it is not defined, then that function is actually not is saying that from this interval, if the function is defined, it is increasing. From that interval, if the function is defined, it is decreasing. But the only thing that I want you to realize is that a natural log is only defined when what is inside is bigger than a 0. So if, let's say, we look into this function, this is an increasing function. If I plug in a 0,5 here, right, a 0,5, squared is going to be 0.25 minus 1, will get a negative number. You cannot plug in a negative number inside of a len function. That is why this one here is not correct, because we know that f is not defined at these points. I hope you get what I mean, because here if I were to plug in any value that is between -1 and 0 and plug it in the original function, you will find out that this function here is not defined at that point, and it is not defined at that point. I am talking about the domain of this function. The domain of this function is actually saying that at these points the function is not defined, and also at this point the function is actually not defined. That is why I'm saying we cannot say the function is increasing when it is not defined. So these 2 points the function is not defined, but if it was defined the function will be increasing. That's what I want you to realize. So this problem was not only based on determining where the function is increasing and where it is decreasing. I wanted you to also see that it is also important to also talk about the domain. Is this part, when you're plugging it in, part of the domain? So this point and that this interval and that interval is not a part of the domain of this function. Hence the function, we cannot say it is increasing or decreasing in those two. So this one here is not a part of this, and this one is not part of this. So the function is decreasing here and the function is increasing there. That is what is important. Here it is not defined. So you can see now what is important here, and then we have described those two things that we wanted to describe. And then the second the Roman figure 2, what was it actually saying? So Roman figure 2 was saying use the first derivative test to classify the critical points. So what is important here is because you can see that at this point here, so you can see that there is actually a point here which is minus infinity to 1, and then there's also another point here. There is this interval here, right? So if you look at this interval, they are telling you the function is actually decreasing. So because this function here is decreasing, we don't know what is happening here, which means it is decreasing throughout until here. So at this point here, whereby we're actually having the x value which is -1, the output here, because if I am plugging in here a -1, -1 squared is going to be 1, and then here 1 minus 1 is going to be 0, and a natural log of 0, you can even test it. If you have a 0 here, you can see that it's going to say you are crazy, I cannot deal with that. So we are having this and undefined output. So at this point, or I can say this point here and that point there, they are both not I can do that, or I can just say, because both these points are undefined, I can say that when x, or at x is equal to -1 and at x is equal to +1 or just a 1, we do not have a local maximum or local minimum. Because why we don't have this, for us to actually know that this is a local min or max, we want to actually end up saying that we must have one sign this side and another sign that side, but this part here is actually not defined. This side here is actually f is not defined at those points. So we only have the sign on one side of each of these points. Hence, we don't have a local maximum or min. I want you to understand that here we are actually not having a max or min because we don't have a sign this side that is telling us that there is a local min, and also this side you can see that at this particular point we don't have a sign on the left that is telling us that this is actually min or max. We only have a sign this side because whatever is happening here, the derivative was thinking that this function is actually defined, but unfortunately it's not defined there, so we cannot say anything there. And if we are having a sign on only one side, we cannot tell whether it is we have a local min or local max. Hence, we actually end up only at that point. I want you to actually follow this thing through because now we will talk about the second question now, question number 2, and then we want to talk about concavity and then deal at certain things. So I hope you get what is actually happening here. So we'll get at this number 2, and of course we'll do it in a separate next lesson because I don't want this to be too long than it is now.